Hello everybody. So today I will talk about the system design of Bitly. And this is take two of part two of this video. And I will talk about these two topics. So number one, how to make URL short and unique. So these two non-functional requirements. And also I will talk about, okay, this and this. Yeah. And I will talk about the scalability. So I will discuss how I can scale the system to 1 billion URLs and 100 million daily active users. So that being said, let me get started with the first one. Okay, so I will talk about how I can make the URL short and unique. So when user makes a request to generate the URL, the request is routed into this service. And if the user specifies the custom alias he prefers, this service tries to save it in the database. And because of this unique constraint here on alias column, it fails if that alias is already taken. So in that case, this URL generation service returns the 400 status to the user. But the creation succeeds. This URL generation service returns the short URL whose alias is the specified one. But if this alias is not specified, this generation service creates the random value here, then save it in the database. If that alias is already taken, database query response returns the error status. So this generation service creates the random value again and tries to save it again. And it retries until the saving succeeds. And after that, this generation service returns a short URL with that random value. So theoretically, this should work, but there are some problems and discussion here. So number one, what is the random value? And number two, what should I do about the recurring collisions? So I have to take care how I can handle this. Yeah. So, okay, I will talk how I can create the random value. And if I could make this random value very likely to collide, it's much better, obviously. So what I can use here is using the snowflake ID. So snowflake ID looks like this. So it consists of 64 bits and 41 bit and this 12 bits are used for the used to represent the timestamp. So the timestamp is millisecond level. Yeah. And for this one, there is machine ID here. So if the ID is created on different servers, they will never collide. So this snowflake ID ensures the randomness, or I should say almost no collision. I say almost here because if the timestamp is time when the ID is generated collides with millisecond level and also machine ID collides. So which means that the two IDs are created on the same server, two IDs collide. So I would say I cannot avoid the collision completely, but as I can see from this, it's very rare that IDs collide. So yeah, it's a good point about this snowflake ID. So, but as I said, there is a quite small, but still there's a possibility that the two IDs collide. So we still need the unique constraint on the alias column and also the retry logic. Yeah, so this snowflake ID is something I can use. So with this, yeah, this problem is, yeah, solved. So about the randomness, so I will clarify the meaning of the randomness here. So randomness is, let's say there is a user who creates the multiple IDs, short URLs at the time. Let's say the short URL created are /001, /002, /003. In this case, I don't say it's random because let's say there is a hacker who opens 001 and oh, what happens? What's I mean, how about 002? He tries it and he finds maybe similar document. And the problem here is the user who generated the short URL. I mean, what he was trying to do maybe identified by the hacker. So that's the problem. But here, I'm pretty sure this snowflake ID helps to introduce the randomness. Because let's say the user create one, first short URL and then tries the next one. Because this is the millisecond level, there is enough, difference between, this sequence number part is refreshed. So it begins from 0 to 4095 and then goes back to 0. Yeah. So this sequence number part gives a kind of randomness. And also machine ID too, in a sense, because if the request, that user's request is handled by different servers, this machine ID differs. So I can say this snowflake ID introduces the randomness. Yeah. Okay, so snowflake ID is good. But something I can say is this shortness here is kind of not met because snowflake ID is, composed of 64-bit. So if I use the base 10 number here, the biggest alias becomes this number. So this is too wrong. Yeah, this is not short. I don't say this is short. So what I can do is, after creating the snowflake ID, we use the base 62 encoding. So with base 62 encoding, each character in the alias is one of 64 characters. So 0 to 9, digit or alphabet A to Z or capitalized A to Z. So now I can say the number of, the number of unique alias is, so it's like this, 2 to the 64 as I showed. Yeah, and because each character each character can be 62, one of 62 characters, so I take the base 62 log and I get 10.74 something. So now I can say the alias is 11 characters. So this is kind of short enough, but I can actually make it shorter. So for that, I use the kind of custom snowflake style ID. So what I mean to say is, for example, here we have machine ID 0 to 1023. But if the number of machines is less than that, we don't need 10 bits here. Samely, timestamp. If this service assumes that this should support only 10 years, we don't need 41 bit. Yeah. So in that way, I can kind of trim unnecessary bits, yeah, of this snowflake ID. So with that, I can reduce the number of bits, which means that we can reduce the number of generated alias characters. Yeah. So that's something I can do. Okay. So the second approach I can say is I can use the kind of counter approach. So let's say this URL generation service first three creates the /0, alias 0, alias 1, alias 2. But the problem here is because this is a digit, so if I create 1 billion URLs, the last URL should be like this, so it should be 10, yeah, characters. So this counter approach with this, I mean, this is not showed. So I can use the base 64 encoding from here. So the base 62 encoding. So with this, the number of characters is, yeah, 5.02122. So this becomes, by rounding up, so 6 characters. Yeah. Okay, this is short enough. And actually, I cannot make it shorter than this, as long as we use special characters in the alias. So this is short enough. So, but still there's a problem. So shortness here is met, but randomness is not met. Yeah. So because as I said, the alias is created with the counter 0, 1, 2, 3, 4, 5, and then this is base 62 encoded. So even after the base 62 encoded, the strings are sequential. So what I can do is applying kind of mapping here. So here I can say number to number. So this number, argument number, should be 0 to 1 billion because we create 0 to 1 billion. Sorry, up in total 1 billion URLs. And this mapping maps the counter number to some number in 1 to 1 billion. Yeah. So in that way, the randomness is met. Okay. So that's something I can do here. Okay, so we need the counter here. And yeah, that's something I can do. Okay, so both of these works, but I would go with the counter approach. So because in reality, I can say this kind of alias custom ID logic is a bit complicated. Yeah. We have to make sure that the length of the generated ID to be minimum, but still I have to make sure that we don't waste the ID. I mean, let me say, so if we'd like to make the alias shorter, it means that we cannot waste waste the ID. So we have to make sure that we create the ID without wasting, ID. So that's a kind of complicated logic. But this approach is quite simple. We just have to use the counter and increment it, and then do the mapping and also basic default to encoding. So I will go with this. So for this counter, I will use Redis. So this Redis counter keeps track of the max number, max counter which was used. So like this can say increment counter and fetch. Yeah, so in that way, this URL generation service gets the counter, which should be unique, and then it does the mapping and then base 6 to T2 encoding. Yeah. Okay, so I explained 2, or I should say maybe 3 logics, or I should say algorithm I can use to generate the ID, which should be short and random and hopefully no collision in the first try. Okay, so now we'll talk about the scalability. So this number. So I will talk from 3 perspectives. So first 3 throughput. Then I will discuss from the spike of the throughput. Then I will talk about this from the storage size. So 1 billion URLs, 100 million data active users. So I focus on the throughput discussion of the redirect request, because one generated URL is clicked by many users. Yeah. So, and especially if the generated URL is included in the, let's say, tweet of the celebrity, like Taylor Swift's tweet, it is clicked by millions of people, possibly. So I can say this is completely read-heavy system. So I focus on the throughput of this redirect service. So let's say 100 million data active users clicks the link on average 1 time. Yeah. In that case, there are 100 million clicks in a day. So 1 day is around 10 to the 5 seconds. So I can say this should be 1K requests per sec, redirects per sec. Yeah. So what happens is user makes a request and server makes a query to DB and gets the mapping recode, and then this returns the response, HTTP response to the user. So 1K requests per sec. So for API gateway, this is totally fine, because internally API gateway is a fleet of servers, so it internally horizontally scales. For URL redirect service, this is totally fine, because on average, one EC2 instance can handle around 1000 requests per sec. So actually one server is fine, but I will use the auto scaling here, because firstly for the spike, which we'll discuss later, and also for the availability. Even if a single server, one server dies, there is another one living. So yeah, availability is guaranteed in this layer. And for database, 1K requests per sec of read request, PostgreSQL can handle it. Yeah, because PostgreSQL can handle around 10K to 50K read requests per sec. So this is fine. Okay. So I will talk about the spike. Let's say this request per sec becomes 100 times. So in this case, what happens is that firstly, API gateway is fine, as I said. URL redirect service is fine because I already introduced the scaling out. I can use the auto scaling to scale these servers according to the CPU usage or memory usage. Yeah. And for PostgreSQL, 100k requests per sec is not handleable by a single PostgreSQL. So what I can use is I can introduce the read replicas because this is read queries. So with maybe 4 to 5, maybe 5 or something, 5 instances of read replicas. Now, even in the spike, the request can be handled. Yeah. And also, this read replicas is useful for the availability here, because if, let's say, the primary node goes down, in that case, read replicas are automatically promoted to the primary node as the automatic failover. So yeah, that's something I can use. Good. Okay. But actually, I don't have to use so many read replicas. Maybe one is fine. Instead, what I can do is, obviously, I can use the cache here. So I can use this cache as a read through cache. So firstly, URL redirect service checks if the mapping, is in the Redis cache by looking up the record with the alias. And if it is not found, it tries to fetch it from the primary DB. And if it is found, this redirect service stores it in the Redis cache and then returns the response to the user. So that's how read through cache works. And I can use it here. Because Redis can now handle around 100k requests per sec. So yes, this throughput as a spike can be handled by this Redis cache. If this is not enough, what I can do is I boot up the Redis cache in each server in memory. So in that way, each Redis cache, receives only 1k requests per sec. Yeah, because each server accepts only 1k requests per sec, as I discussed. So yeah, Redis cache can completely handle the throughput of the spike. Okay, so that's something I can do here. And I just want to quickly mention that I don't use the CDN here. So CDN is the kind of cache in the edge location in each region. So let's say I open the link from Japan. In that case, the edge location in Asia or maybe in Japan, which is physically close to me, caches the result. So from the second user in Japan, the response is returned as the CDN layer, which is before API gateway. So it becomes much faster. So we don't need to, the server side is not heavy loaded. But I can't use the CDN here because, as I said in the API discussion, I use 302 redirect status because we wanted the metrics of the request. So at least the request should come to our API gateway to log the request. So that's why I cannot use the CDN here. Okay. finally, I will talk about the storage size. So let's say each record is 100 bytes, and there are 1 billion URLs. So it should be in total 100 gigabytes. Yeah, so this URL mapping table becomes 100 gigabytes, which is totally fine because nowadays PostgreSQL, like AWS Aurora, can store 512 terabytes of data. So yeah, this is totally fine. So we don't need the sharding or something. We don't need it. Oh, and one more thing. I forgot to talk about this Redis counter portion. So even though the request per sec, the throughput of the URL generation service is lower than redirect service, I would say I use auto scaling here. Yeah. Mainly because of the availability reasons. Yeah. I don't want to make this servers a single point of failure for URL generation. So if I do that, this counter, what I should say? Yeah, this counter, each server tries to get the next counter. So yeah, this works. But I just wanted to mention that there isn't a race condition. Let's say there is one server who tries to get the next number. There is another server who tries to get the next number. But those requests are handled completely sequentially, serializable way. So there isn't a race condition which occurs here. So actually that's why I use the Redis counter. So yeah, that's something I can do. And okay, I will quickly calculate the requests per sec. There should be 1 billion request URLs to be created in total. Let's say this is created in 5 years. So in a year, there should be 200 million records in a year. So by around 200 million in a month, around 1 million in a day, and 1 day is 10 to the 5, so 10 URLs per day. So assuming that, sec. Yeah, assuming that this URL is created, 1 billion URLs are created in 5 years. In each second, there are 10 URLs created. Yeah. So this Redis counter can completely handle 10 requests per sec, so it's totally fine. But if this becomes a bottleneck, I confirm that it doesn't. But if this can become a bottleneck, what I can do is this increment counter, I will make it the bulk counting, bulk update. So each server fetches next 100 numbers, counter numbers, and increment by 100. And then this URL generation service doesn't have to make the request for each URL generation. So that's something I can optimize if this part becomes a bottleneck. And also for the durability of this part, of course, we have to keep track of the Redis durability. Of course, we have to keep track of the counter, even if the Redis go down. So I can use the append only file of Redis. So I can For durability, I can use the append file. So I configure, what was it? Append file sync to be always. So with this configuration, when the record is added into the Redis, or in this case, if when the counter is incremented into Redis, it also writes the log, write that log to the append-only file, and when that persists, wait, what was it? Okay, so persistence. So when that log record persistence is done, Redis returns the response. So in that way, the current counter, or I should say up-to-date counter, is always logged in the persistent file. And for the availability, I can use the read replicas plus automatic failover. I will enable this. So with this, even if the primary node goes down in the Redis, it is failed over. It automatically fails over and promote the read replica to the primary node. So availability is highly guaranteed with this. And that being said, probably I will use the PostgreSQL instead of Redis. So the problem I mentioned is because Redis handles the request in a single-threaded way, sequentially. This is completely matches the use case of this counter. But taking a look at this 10 requests per sec, PostgreSQL is totally fine. So I will use this PostgreSQL with the isolation level to be serializable. With this, I can completely avoid the race condition, and still this isolation serializable level degrades the performance of the PostgreSQL, but still 10 requests per sec is totally handleable. And I don't have to think of the durability anymore. And for availability, I can use read replicas and failover in the same way. So I would go with PostgreSQL instead of considering the durability of Redis. But I think both of them totally work, so it's fine, I think. Okay, so that being said, I finished my today's systems design practice. Thank you so much. Bye.